Hey everybody, this is Larry. This is me doing week 5 of the weekly premium challenge. Hit the like button, hit subscribe button, join me in Discord. Let me know what you think about this one. Of course, we have a hard one. It's 2 a.m. I want to pass out after doing 16 miles of running. And of course, we have a hard one. Let's do it. With 1121, divide array and do increasing sequences. Alright, given an integer array num sorted in non-decreasing order and integer k, return true if this array divide into one or more disjoint increasing subsequence of length of at least k or false otherwise. Okay. This is a premium hard problem that I've solved before apparently, but okay. So I think this, if I have to guess, I mean n and k is 10 to the 5th. The numbers always go that way. If I have to guess, this is some sort of greedy. How would I structure it? These problems are going to be either very easy or very annoying. I mean, or I get lucky and they're still very annoying. Okay, so for example, if are they sorted or they just happen? Okay, they do give it to you in sorted order for some reason, which is fine. Okay, then now we put it in for every number. So we have one at least k, right? So that means that for every number. How do I want to think about this in terms of greedy? Okay, so for example, we have 1, 2, we have 3, and then 4, and then we have 2, 3, 4 for the first one, right? They have to be strictly increasing. Yeah, okay. That means that when you get to the next two, you have to start a new one, 3. Maybe you do a greedy. Well, here you want to finish this off first, and then next one 3, and then 4, and then 4, right? I mean, I don't know. This seems kind of awkward. So you have 5, you have a 6, greedy 6, 7, and then maybe 8, but you're no good, right? I think the key thing about these problems is try to figure out an invariant, something that doesn't change, that you can build off for it to be good, right? I think it's gonna be something like this, but I don't know how to like define it precisely. Because you can also imagine that maybe you have like I don't know 5 and 6, then actually you just kind of or maybe just something like 1, 2, 3, 4, 5, and then just vote these into here, right? So then the question is, and then maybe if you have another 5, then what? Well, then you would put one of the 3s in here, 4, 5, right? So then, so you do it that way. But how would you figure it out? Honestly, I don't know. Like, you have to figure out how to combine them, and then do we just always divide them out? Business, because if you just do something like lazy, right? Like given this exact same input, if we do something lazy, we do 1, 2, 3, and we have 4, 5, and then 5. That's just not good, right? And then there's really no easy way to kind of combine, like you combine the 4, 5 here, or the 5 here, but you need to really redistribute, right? Is it binary search? Binary search on the number of sequences. Is that an idea? Because right now, the hard part about what we're doing now is that we don't know how many sequences we need, right? But what if we can binary search? What if we know that, okay, we have 1, 2, 2, 3, 4, 5, 5, and we have 2 of them, right? So we have 1, 2, but that still doesn't really solve what I want to say, right? Because then now we have 4, 5, 5, and now we figure out how we distribute them, right? Maybe. But what if we have just like 1 and then 2 and then 3? Because we have 2 of them, we can just redistribute it in this way, right? Maybe that's fine. And then the key thing is noting that, well, obviously you need at least the number of things, but that could be taken out in a binary search anyway. Because then now in a binary search, well, okay, let's say we can, I don't know, I mean, yeah, I mean, binary search isn't quite the right phrase, but it is maybe it's not the right idea. In the sense that, for example, even here, well, 1 is false, 2 is true, but 3 is false. So you have to. So there's like one thing, right? And you can try every number, obviously, like in a linear scan, because that would be too slow, I think. Wait, is that true? I mean, do I need to distribute it like this? If I do it in this way, try 5. No, this just don't have enough, but that's fine. Right, so okay, so here, and then now we break it down to 2. I mean, I have a guess, but I don't know that it is right. And you have this case of 1, 2, okay, 3, 4. Okay, we have something like this, then what? Oh, well, you just have 1, right? So you have to 1, 2, 3, 4, 5. Okay, so then maybe we do something like f is equal to collection dot counter of nums. That's given. And then the max value is going to be the minimum. But is that always enough? Because that's the width of the thing, right? I'm just going to YOLO this because I can't prove it, like a lot of greedy things. But okay, so you have the max value, right? So that means that we have at least this times k if this is less than or equal to length of nums. Let me just return this, right? I don't know if this is true. YOLO submit. Give me a wrong answer. Okay, I don't know. I mean, it definitely is hard. I think the observation is, well, I mean, I think this one makes sense. I think well, let me step back for a second. It makes sense in the sense that if this is true, or this is sufficient, or maybe the other way around. Like this is, yes, this is necessary, but like it's easy to prove that this is necessary, right? But it is not easy to prove that this is sufficient. I think that's the part that I'm struggling with, right? And what I mean by that is that, I mean, you know, if what this is saying, what I'm doing, and I just kind of YOLO'd. I didn't explain it because I didn't have confidence in it, to be honest, right? And the reason why, you know, max of the f values means that the most frequent element, for example, if you have a number that appears 10 times, that means you need at least 10 subsequences, right? That's basically all this part is saying. And each one of these has to be at least length k. And some of that formulation is just coming from just going, you know, like if you do it in a round robin kind of way, then if you construct that in a round robin, then it's always going to be non-decreasing, going from left to right, or increasing even, because, well, from the pigeonhole, or lack of a pigeonhole maybe, because this is the max value, no number is going to appear twice in the same row, or subsequence, if you will. And as a result, this will always be true, right? So that means that if this is the number of rows you need to have, and this is the number of elements you have to have on each row, so then this is the number of minimum required elements. But it's hard to prove that this is like sufficient, right? Like it's easy to prove that it's necessary because this is the minimum amount. But how, you know, I guess the way that we did it, kind of visualizing it, is kind of the way to do it, in that you just do a round robin, and as a result, this will always give you the idea is that a round robin will always give you non-decreasing order, right? And then the only thing that makes it increasing strictly is if each row has to have non-duplicate elements. But honestly, this is hard. Like, I don't know, what did I do last time? How did I do it last time? It was only a year ago. I don't remember this problem at all. It seems harder than... okay, I guess I did do it the same way, basically. 1 3s, 1 2 3s, and then just... I don't know. I have to watch that video. I mean, this is basically the same thing, right? I mean, I just kind of... same idea, but... I don't know. I don't know what to tell you, friends. Yeah, let's take a look at the hints. I mean, again, I know how to show it as necessary. It is just the sufficiency is a little bit trickier. I mean, I guess I knew it was greedy, but I thought maybe there was some stuff with binary search. But the binary search idea did give me an idea, because I was thinking like, okay, if there was a binary search, how would you do it? Well, in fast enough way, and then you just round robin. But getting the round robin from that opened the door to the solution. And of course, this is linear time, right? You have to go through every encounter. This is also linear time, and this is linear space as well. But otherwise, pretty straightforward. Yeah. Well, I mean, I guess you don't... Yeah, I mean, I did it in linear time, linear space, right? But you can actually optimize away the linear space now that you proved this. I mean, this is just easy to write, but you can just do a linear scan to get the max frequent or the most frequently seen element, right? I don't know. That's all I have for this one. Let me know what you think. Thanks for watching. And yeah, stay good, stay healthy to your mental health. Have a great week, everybody. I'll see y'all later and take care. Bye-bye.